Okay, so thank you all for coming. It's a pleasure to introduce Cayman Unterborn. Cayman is coming to us from the Southwest Research Institute, where he is a research scientist. Cayman got his bachelor's degree and PhD from The Ohio State University. His bachelor's in physics and astronomy, so he can talk to people like me. And then his PhD in geological sciences, so he can talk to many of you. Then he went to ASU as an exploration structural fellow and an assistant research scientist before moving to SwRI. So take it away, Cayman.
Thank you. And I'm actually still at ASU. I've got special dispensation to stay in Phoenix. And so today I'll be talking about, I actually realized, of course, during COVID times, I gave an online talk to this group on a very similar topic. And I realized that about Wednesday. So I've added some extra stuff. This is work that Brad Foley and I have done with Steve Desch, Patrick Young at ASU, thinking about the concept of time in rocky exoplanets and how that's going to affect our interpretation of the geological state and the potential habitability of these planets. And I think it's a cool topic because it bridges a lot of astrophysical models and astrochemical models with some bread and butter geoscience. And it really shows the power of how simple models from geoscience can really help us inform astronomical observations. So I always like to start my talks by congratulating you on finding a planet. And in this case, you are maybe a sleepy geologist and have discovered the Earth. And you have a wealth of data at your fingertips. You've got lab data that shows you phase diagrams and phase equilibria, knowing what the rocks in the deep interior are made of. You have figured out through a long time of research that the Earth's mantle is convecting, that it's undergoing plate tectonics. You have some sense of the petrology on the surface, what the rocks are made of, what its chemistry is. Things like weathering and climate. You have some sense of this. And then perhaps most importantly, you have the concept of time. You have the geologic timescale. You either have a fossil record to go back to, or you have some mostly isotopic data trying to tell you about the history of the Earth's past. So you, much like I did in graduate school, decide to get into exoplanets, and you think you found a really cool Earth-like exoplanet. It's actually probably looks more like this. It's super dim. You don't really see it. But I'm going to give you the best case scenario. And you've discovered basically every observable we have for an exoplanet. And I don't know of actually any that have all of these, but I'm going to give you the best case scenario. This is what I think you can get, and this is maybe an old list. You may have a few more. But direct observables, you should hopefully know its mass and radius, which will give you its bulk density, so you can kind of figure out what it's made of. In the era of JWST, you might even have the atmospheric composition. It may not be the best, but you at least know kind of what it's made of. You certainly would have its orbit if you have those. You'll know a lot about its host star. And in the best cases, you might have some direct imaging and get some other interesting aspects of it. So this talk is all about connecting models to observables. And so you want to understand, really, what is that planet you've discovered made of? How does it evolve through time? Does it have plate tectonics, mantle convection, these kinds of questions? And so you look to your models and you try to understand planet size and compositions. This takes you to the classic mass radius models that have been done for 2 decades. Host star composition, which is something I've worked on a lot, trying to understand how the formation of planets affects planetary chemistry. You can even go into formation models. This is work from Jade Bond from a long time ago, but trying to understand how the chemistry of exoplanets will change as material mixes in your disk. And you have lab work. So this is actually looking at the composition of an iron core. I will not explain this figure. It's a lot of mineral physics, but understanding how the chemistry of your planet as it starts in a magma ocean, how much material gets segregated into your iron core versus stays in your mantle. Problem, however, is your models aren't that great. Mass radius models are known to be degenerate. You will very rarely get a good sense of what a planet is made of just from mass radius models. Host star compositions, I'm a big fan of it. However, it is indirect evidence. You're kind of relying on some chemical quirks for that to be true. that can you observe formation after a planet has formed? You're really seeing the aftermath. Core formation is maybe observable, but it's got a lot of assumptions, and perhaps at the observational resolution we have, you may not even observe. However, it is very important for your planet's evolution. And I say planet evolution because here's a figure I made that ended up being used in the decadal survey, kind of showing for sort of the top 10 elements we care about, the complexity of all of this. So you have a planet that's right here. It's a solid mantle, it's doing stuff. You have to go back in time and understand how material condensed in the disk, how it mixed, how those planetesimals then mixed, and is material ejected and you're not seeing it. Then you have core compositions. Your planet actually is a magma ocean. The core equilibrates with the mantle, hopefully, gravitationally segregates to the center of the planet, takes a lot of the iron with it, leaves behind a depleted mantle. Now you have your magma ocean. Things are ingassing and outgassing. That's going to change things like your mantle fugacity and its chemistry. And then eventually, in the ideal case, your planet solidifies, and you've got now a carbon cycle. You've got material that's able to go into the mantle, come back to the surface in the convecting mantle, melt, degas, things like that. So the exoplanet you discovered, if your question is it habitable? You need to understand almost every step in this to at least get some sense. And this is all models. Your observables are not going to help you all that much. You do have one thing going for you, and that we have many, many, many exoplanets. So if you're trying to understand planets as a whole, maybe not your individual exoplanet, you may be doing something, you may be able to do something that we in geoscience were never trained to do, which is think about demographics and exoplanet demographics. Even our solar system is perhaps not the best indication of what planet demographics can be. You also, on top of that, the most important thing is the number of exoplanets almost always goes up. It rarely goes down. It has got down, but it almost always goes up. But I think most importantly is you have many, many, many stars that do not have known planets. That doesn't mean they don't have planets. It just means we have a lot of data from the astronomical side, that we can also utilize as well to understand planetary and stellar systems as a whole. And I'm going to talk to you specifically about one aspect that I think, again, bridges this gap really well, of looking at exoplanet climate and the presence of an atmosphere to tell you something about how that planet formed or whether it's habitable today. So over here on the left, I've got plate tectonics. This is essentially just cartoons of the carbon cycle. I'll just give you a brief tour of what the carbon cycle is. So on a plate tectonics planet like the Earth, you have carbon, CO2, whatever your form you want, outgassing out of volcanoes. Material has melted. Carbon that was in the melt has exhaled and gone into the atmosphere. Some of this eventually ends up weathering onto rocks, which eventually gets turned into carbonates on the surface, which eventually gets weathered into the ocean. Some of this amount of this material is able to go down via plates. Some of it will get back out in arc volcanism, but some of it will presumably go back down into the mantle, hang out for a while, and eventually come back up. We also have stagnant lids. You don't have plate mechanisms to bring material down. However, you do have just, in this case, material as it cools and turns into rock from magma will eventually become so dense, it will eventually return itself back to the mantle to get entrained and come back up for volcano. This is a less efficient process, but it does work. So this is the surface weathering, material comes down, comes out. You can also have things like metamorphic degassing, where essentially the surface gets hot enough or the surface pressure is high enough that the solid rocks will release their carbon. And so when you talk about the carbon cycle, you're essentially talking about climate. And so on Earth, we have this nice, presumably regulated carbon content that has given us billions of years of habitable conditions. You can think about cases where you don't have enough carbon and you end up not being able to support a greenhouse, and you can turn into a snowball. And on the opposite end of the spectrum, you have something like Venus, which is not able to regulate its carbon content. It spit a lot out of it into its atmosphere, turned into a hothouse planet. And so I'll give you a more a graph version of this. So this is for a stagnant lid. On the x-axis here is time. On the y-axis is a few different things. I want to explain the curves first. So the black curves are all the degassing rate. And the orange curve here is what's called the supply limit. You can think of the supply limit as if your degassing rate goes above this curve, you're building up carbon in your atmosphere, you're not drawing it down enough, and so you're going to increase your partial pressure of CO2. So in this case, looking at the snowball planets first, one way you can do this is you're degassing just fine, but eventually your planet sort of isn't able to melt anymore. And you have no input of carbon into the system, so you will essentially not be able to really support a temperate climate and turn it into a snowball. And you can see this in the partial pressure of CO2, which just tanks until degassing ends. These are extreme examples. On the hothouse end, of course, sometime in your history, you have exceeded the supply limit. And even though you stay above it the whole time, your CO2 builds up, your temperature goes up, you can see that. So those are just some things to keep in mind when I talk about snowballs and hothouse climates. This is what I mean. It really all ties to the supply limit and the degassing lifetime. So I mentioned this already. Habitable planets are warm planets because you need heat to support all of this. And heat on planets comes from a few different sources. The first one is accretional heating. This is just building your planet, gives it heat. When the core segregates from the magma ocean, you will get a gravitational release of heat. The one I'll be talking about today is the decay of the radionuclides, uranium, potassium, and thorium. And tidal heating is something, you would presumably see this in your observational data, or you can infer that it has tidal heating, but not all planets have tidal heating. That's why it's in parentheses. So we're going to talk about the radionuclides today, and I want to give you a quick, just some information about the radionuclides we'll be talking about. So there are short-lived radionuclides like aluminum-26 that are very important to planet formation, but their half-lives are so low that for gigayear timescales, they don't really make a difference. But thorium has a half-life of 14 billion years. The two isotopes of uranium are very different, 4.5 and 0.7. And then potassium-40 over here has a sort of intermediate half-life. But you can also look at the power per kilogram. And so thorium is kind of middling. 238 is higher. This one's very high. And potassium is also kind of right in the middle. And of course, these decay with time. So here is the Earth's abundances now. And if you were to go back in 4.5 billion years, this is what it was. And that's just taking into account the half-lives. The question, though, is, those were the Earth abundances I showed at the end there. We, of course, this is the classic SwRI. We have many exoplanets. Do they all have the same range of radionuclide abundances? And is that a question that's answerable? So we asked that question in 2017, or 2015, I think is when this paper came out. So interestingly, when we looked in the literature when I was in grad school, we couldn't find radionuclide abundances for planets with stars, or stars with planets. And that's because the thorium abundances were often used for very metal poor stars to try to date them. But I don't think the connection had been made between, well, these radionuclides are also super important for exoplanets. So we went out and measured it, and for a sample of, I forget, of 10 or so solar twins, so these are metal-rich stars similar to our sun, and essentially just looked at, does the thorium abundance vary star to star? So here, we'll just look at the right-hand figure. So this is the abundance of silicon versus the ratio of thorium to silicon. The triangle here is the sun, and then stars with planets are in black, stars without planets are not filled. What's interesting, though, is that you see a factor of 2 variation in this ratio. And I'm talking about ratio specifically because we talk about concentrations, not absolute abundances of radionuclides. So we think about it in this, but relative to the sun, there's a factor of 2 variation in thorium. And you can reasonably ask the question, well, if you have, okay, sure, your ratio is high in the star, how does that reflect in its planet? And this is one of the chemical quirks I mentioned earlier, is that when you look at the the cosmochemistry of how planets form and how elements condense from a gas phase into a solid phase, thorium, uranium as well, tends to condense with silicon. So their ratios never change, or they change very little. It's roughly so if you were to look at the magnesium and silicon are both refractory elements, the sun and the earth are almost exactly the same, like 1.05 versus 1.15, very close together. And we think this should happen in other planetary systems too, just because of how we think planets form. Right, so there's going to be a little difference. So thorium shows back in 2015, oh, that's right, yeah, 2015, we found this factor of 2. And in the intermediate times, another group came along and measured the same thing and found, so this is now I'm normalizing to magnesium relative to the sun. They found this, of course, the same factor of 2 variation in thorium abundances. Now, uranium, so thorium is hard to measure in metal-rich stars because it's very near an iron line. Europium is even harder, or sorry, uranium is even harder to measure because it's really in the middle of a giant iron line. But you can look at nucleosynthetic studies and show that the europium to magnesium ratio relative to the sun is extremely similar to what you would expect the uranium to magnesium ratio relative to the sun to be. So you can use this as a scaling factor, which is what we're going to do. And you can see, yeah, about the same factor of 2 difference in the thorium abundances. Potassium's harder. So we can certainly, potassium's easier to measure in stars, although I was still surprised at how low that number was. This data comes from the Hypatia catalog. It does show a lot of variation in the bulk potassium to magnesium ratio. However, 2 things, unlike uranium and thorium, potassium's abundance in the Earth is about 80% smaller than the sun's. So this is what we call a moderately volatile element. So some fraction of it has been lost either due to planet formation or it's been sequestered in another reservoir in the solar system. But also only one isotope of potassium is radioactive, and it's about 0.001 or 0.001% of all potassium is radioactive. So this bulk abundance isn't telling you anything about the actual abundance that would end up on the planet. You have to take into account this depletion in this potassium 40. And as I get further along, I'll show that those matter a little bit, but not all that much. So that's the distribution of heat budgets we see. This is the system to system variation. But of course, in this orrery, not all planets are the same age either. So we're going to be seeing them at different times in their geologic evolution. And so that also means when you take into account the production rate in galactic chemical evolution terms of these elements, they also vary in time. So we had more supernovae early, so we would presumably have more of these radionuclides just because the production rates are there. So this is something Elizabeth Frank looked at in 2014 that we built on in our 2022 paper. And essentially now this time here is the time of the planet formation in galactic history. So 0 is Milky Way, 8 is when the Earth forms, and 12.5 is today. And from her model, she modeled out the production rates and decay rates and all of this, as well as the enrichment due to the production of magnesium and silicon that would dilute your concentration. So you have kind of 3 different axes going on here. But essentially, if you just look at mantle concentration, potassium is the highest over time. Then you get thorium, 238 and 235. Now, if you were to now, that's just the concentration. If you now convert it into heat produced, so this is if you formed a planet at 4 billion years, here's how much heat would be coming from those elements. You can actually see that early in galactic history, uranium-235, we had a lot more of it and a higher concentration, and it produces an order of magnitude more heat, so it's higher. Then potassium, which eventually takes over, and then 238 and thorium are always towards the bottom. And this one just shows you kind of the relative ratio of each of them. So this is showing from galactic chemical evolution models that you have kind of system to system variation on top of temporal variation. So you need to know when your planet was born to get a sense of where it fits on this graph. So what we wanted to do, right, this is kind of what I was saying. So in this case, this is time after galaxy formation and your starting heat production. And this is just 4 different curves. So if you were built at 0, 4, 8, or today, this is your heat production rate through planetary time. So you're born with this much and you can see it decay over time. And you can see, these, a planet born at 12.5 versus today still has more heat. And so the question is, does that mean it's still undergoing mantle degassing or questions like that? Right, well, that's what I was going to say. So you can ask questions of where you were born and when you were born. How long would your degassing last? And the question then is, are you degassing today when we observe it? If we talk about habitable planets today, that's kind of the question we're interested in. So to do this, Brad Foley has this great one-dimensional mantle convection model that he has built a lot of bells and whistles on top of for this work. And essentially what we're going to do is we're going to pick a time in galactic history, and we're going to use these system-to-system variations as kind of, we're going to Monte Carlo and just pick abundances. They're not correlated. They probably are correlated, but we're not considering them correlated. We're going to pick abundances, run it through time as in that previous figure, and then compare, and then ask the question, when does the temperature at the wherever your melting surface is low enough that you stop degassing? And we have a few other parameters here. Reference viscosity, so you can think of this as, for lack of a better term, how sticky your mantle is. So it's high viscosity, it will take longer to get moving. Lower viscosity, it will go faster. Initial mantle temperature, so this kind of comes back to the accretionary heat. We don't know what temperature planets start at, so we're going to sample through a distribution of starting temperatures as well. And like I said, we have a few assumptions. We're going to pin the potassium-40 ratio to Earth. We're going to choose that same 80% depletion, and we're going to assume uranium and thorium are perfectly refractory. And it is, of course, a function of when the star is born. So I'm going to start with a planet that formed at the same time as Earth. So on here, I plotted this Q naught term is essentially the total heat budget from all the radionuclides added up relative to the Earth's initial abundance, which is about 100 teratons. And then on the y-axis is the age of the planet when degassing begins. And I put it the 95% values here. All values fall within that. So you can see kind of a linear-ish distribution spread out, fanned out with heat budget, which kind of makes sense. If you have more heat budget, you should degas longer, but there is some thickness to this. Reference viscosity over here, this is just your scaling factor for everything. Of course, the higher viscosity you have, the longer it takes you to get spinning up, but actually that helps you keep your heat low and slow longer, so you keep degassing. But interestingly, mantle temperature doesn't really change all that much. And here's for a 6 Earth mass planet, and they look similar, but you'll notice that the ages are much higher. And this comes down to, we're talking in concentrations. So these actually do have more radionuclides, which means more heat. But when you take into account things like surface area or pressure gradients, it doesn't really matter. So you actually do end up degassing. Well, it does matter, so you end up degassing a little bit longer. So just looking at those 2 parameters, viscosity and this heat budget term, we can better see, and the colors here is the degassing duration or age when degassing ends. And I plotted on here today. So this is the same planet that formed 4.5. This is the 4.5 billion year contour-ish. And so if you wanted planets degassing today for a stagnant lid, you actually need very high heat abundances, which is interesting. The Earth's, of course, in a plate tectonics regime, which helps thin the lithosphere, which helps melting last longer. That's one of the aspects, whereas a stagnant lid probably wouldn't be degassing today unless you had very high abundances. You can get away with it with higher mass planets, kind of like what I said earlier. Oh yeah, and there's the confidence intervals. That this is 90% of all values fall within those 2 lines. And so this is a lot. I don't really, you can ask the question, okay, if I need Two. 2 times the Earth's amount. You can ask, given these distributions of abundances, which one is more likely to provide me that amount of heat? And this will kind of tell you which radionuclide is most important to this story, especially given that we have different heat productions, different half-lives, and all of these other things. And essentially what it comes down to is, this is age degassing ends versus viscosity again. And then if all of your material came from potassium, you actually have a higher probability of that than 235. And that makes sense. 235 has a short half-life. It produces a lot of power, but it's just not very abundant. So this is kind of just inverting these distributions. But you do see some spots where the probability is low, but on these 238, if you need really long degassing lifetimes, have a high viscosity, uranium can actually power you for that long. But what this is telling you is what you're seeing on this event is sort of the rarity of events. And so your most common events are things where potassium is dominating. In this case, the planet's initial potassium abundance, which should presumably be observable from its host star, with some assumptions on volatility and all that, is going to dominate most of the planets we expect to be degassed. Higher mass planets, you can have some uncommon cases where uranium and thorium are necessary, can do it, but you still need a high abundance of uranium and thorium to do that, an uncommon amount of uranium and thorium. But again, you can measure this. So if you were able to say, hey, planet I just discovered, I'm going to measure its host star abundances, and I see it has a subsolar thorium abundance, this model is moot. But if it has a supersolar amount, you could be thinking, okay, this is using stellar abundance data to tell us something about what we might expect for the evolution of that star. And so if you're trying to find targets for potential atmospheres, and not saying it's direct observable, but it's certainly evidence that you might have something interesting in your hands. Oh yeah, I mentioned that. So, okay, so that was one time period. Now let's combine the two. Let's randomly sample within these distributions, pick a time in galactic history, and actually ask, when does the degassing lifetime, how long does degassing last as these radionuclide concentrations are changing through galactic time? So here we go. Here's time of planet formation versus mass, and color represents degassing lifetime. I plotted the lower limit of all the values of the 95% values, the upper and the average. And you can kind of see a few things that as planet mass increases, your degassing lifetime goes up. We've seen that. When you form in galactic history, however, your degassing lifetime gets shorter. I guess that's the two things you see. But this just tells you how long degassing lasts. Of course, if it's degassing today, its degassing lifetime plus its age has to exceed the age of the galaxy. So if the sum of those two are greater than 12.5, you expect those planets to be degassing today. So you can turn this into kind of an age question of, this is now, if you have a planet of an age, in this case, less than about 2 billion years, regardless of the mass, it's probably degassing today if it's a stagnant lid with sort of Earth-like abundances of potassium. Anything below this in the stagnant lid case is probably unlikely without a few other things I'll talk about later. Even at the highest confidence, you only gets you maybe 4 to 5, but now you require special cases where you need very high viscosity, which we may not know how to get. And you still need kind of a supersolar amount of potassium and maybe thorium and uranium. So let's compare those to actual planets. And so looking at the average, we found only 2 planets are roughly above the 2 sigma level, likely degassing today, given the uncertainties in their mass and their age. Now, age uncertainties, I've learned, are notoriously unreliable, but I do not think that's a problem. I think that's an opportunity to get better age models. But those 2 planets are Kepler 80e and K236b. I've also plotted on here the TRAPPIST-1 planets, which I'm sure most people in this room know as the sort of poster child of exoplanets. What really spurred this work was when the ages of TRAPPIST-1 came out at to be like 7.8 plus or minus 2.2, I was really reluctant to think those planets were likely like Earth. This is just so old. They would have run out of power. Now, maybe they could have gotten it from other sources, but at least from the radiogenic power, I didn't think it was possible. And so I wanted to show that. And so at least on average, we would not expect a stagnant lid TRAPPIST-1 to be degassing today. And maybe the high viscosity case, even TRAPPIST-1 doesn't get there, but you do get a few more planets. But this is telling you old versus young, even if your error bars are big, is a really important thing to know about an exoplanet, so you can know what to expect. And even when you start digging down into atmospheric composition, I think it's going to matter a lot. Now, this is the part of the talk where I go through all of the other caveats that come with this. So our degassing model relies on a dry solidus. Of course, as you start adding water to the mantle, or you just start adding hydrogen to the mantle, you will lower the solidus, the melting temperature of the rock. I will not go into this figure all that much. You can have changes. This is the change in the age max. You can actually decrease the age max as you, so this, this would be, it gets worse for you before it gets better. Let's say it's not water, it's just for some reason, whatever material you're made of has a lower melting temperature by say 100 Kelvin and 200 Kelvin. You can extend degassing lifetimes by about 1 billion years on average, just by making it easier to melt. But this is kind of an end member case. The melting relationships are very, very complex. Core mass fraction is another one. This is, we're talking in concentrations, so the size of your mantle matters in your calculation. But even changing the core mass fraction doesn't really make all that much of a difference. It's kind of this like 500 million to 1 billion years. The one I really want to talk about, however, is the 40K, the potassium ratio. So let's just look at the red curves. This is the change in the average age max. So if you have the potassium, you actually lose about 1 billion years. If you double the potassium, you end up getting another 500 million. I guess it's 500 million years on either side. But you can see there's it's not a big thing, but it's big. Most importantly is we don't know how much is half or 2 even reasonable. Is it a factor of 10? Is it a factor of 100? One of the things we learned in doing this is we really don't have good constraints on the potassium 40 production rate through galactic time. I think it's even questionable, although not talked about all that much, of how it's produced even. So it's a very big, open astronomical question that I actually, we tried, skip that. We tried to talk about a little bit. So this is work by Patrick Young that was in this 2022 paper, trying to actually model supernovae production of potassium 40. Now, I can answer very few questions about this, but I'll show you the results. This is a fun part about interdisciplinary science is you synthesize a lot of stuff, and this is a 30-page letter. It's the longest letter, I think. Yeah. But essentially, the colors here represent the mass fraction of 40, the potassium 40 ratio. And what's interesting, although I don't think this screen shows it all that well, is you get these really well collimated bullets in the supernova model. And what you're not seeing here is that in these bullets, you actually have a fairly high concentration of potassium 40 compared to everything else. I'm not suggesting there's collimated jets of area in the galaxy that are potassium rich, but it does show that there is spatial distribution possible. So if you were to take this model and integrate over it, and now I'm going to show you the amount of potassium that's in potassium 40 that's in that bullet versus the total mass potassium, you can see kind of this range of potassium 40 to potassium 39 ratios. And you get your highest potassium mass percentage at about 10 to the minus 5. And you can ask, all right, if I have this well-collimated bullet and I've just got the perfect disk right in the way of it, how much is it actually going to increase my potassium 40 abundance? And if you look at an FGK size minimum mass solar nebula, it's only about 1%. M dwarfs, however, because their disk masses are so much lower, can have, 30% is not big, but this is just one model. can have an effect. You could produce perhaps systems with more potassium-40 than others. On the volatility end, that's just a really hard problem. We don't know, we do not know whether that volatility trend is characteristic of all of other systems. I do have some ideas of how maybe you can test it with ultra hot Jupiters, if anyone's interested in that. I think we may get some sense of volatility from that, but okay, coming back to this this age question of how old is too old. I have some interesting things that come out of this. Well, first is tidal heating will of course extend this age. That's kind of it's not a constant power source, but it's a good amount of power that could be added. But you should be able to learn that from the orbital data. You kind of hopefully already know that. The presence of water will change things. That's not included in this model directly. But yeah, I'm not sure about that. What I find really interesting though is this plate tectonics question, which would extend the degassing lifetime. You think of the Earth, it's 4.5 billion years old, but it still has active volcanism. If you were to look at, say, really, really old planets, and you were able to figure out, and I think there's someone in the past has mentioned looking at sort of hydrogen sulfide in atmospheres. If you can use that as a signal, or another gas species as a signal for volcanism, I think you'd have some interesting indirect evidence for the presence of plate tectonics on that. So it's not to rule out all old planets, but you kind of have to know what you would expect. Another example I'll talk about in just a second is, what if you're young or old and have no atmosphere? What does that tell you? That's going to tell you something about either the interior's ability to hold on to it, or the atmospheric stripping rate is extremely high, and you had one, but you lost it. Yeah. And actually, before I go to that, I'll go to that. Let's talk about the atmosphereless systems real quick. So this is work that started with LHS 3844b, Stephen Kane, Brad, and I on a visit to Riverside, got talking about this planet that was recently found to have no atmosphere. And we asked the question, well, why doesn't it have an atmosphere? And one of the conclusions we came to is that, well, it's actually very hard to produce a planet that doesn't have that you would not expect to have. You would expect it to have an atmosphere. Now, the stripping rates could have been wrong, but we basically argued that this is evidence that this planet formed volatile core. And Katie recently had a paper came out that looked at a very high profile planet on this, looking at TRAPPIST-1. And we came to the exact same conclusion, which actually matched previous work I had done on the Earth. Agreed with previous work I had done on TRAPPIST-1, completely independent. And so this is some of her work looking at, sort of the fact that TRAPPIST-1b or C has at least a very thin atmosphere. You can now put constraints on things like the amount of carbon that it had to start with. So this is the volatile core, its viscosity, heat producing elements, its starting temperature. All of these things play a role. And just by having no atmosphere, you actually learn quite a bit about the planet's interior. The other one I wanted to talk about is this, also important for MDORS, is delayed degassing. So one of the things that came out of this model is the age of degassing ends is not just how long it lasted, but also when it started. So we have on the y-axis here is the start time of degassing, and you can see we have quite a few that take quite a while to start. Or I guess this is just like take quite a while to start degassing. These are ones that tend to be cold and have a high viscosity, which I'll show in the next figure. Yeah, this is the same thing. And they tend to degas almost just as long. Yeah, here we go. They tend to degas almost just as long as their counterparts that didn't have delayed degassing. Now, this is important, and this has been brought up by people like Ed Kite and others, that you can perhaps refresh your atmosphere after it had been stripped off, perhaps during early active MDORF evolution. And so this is another interesting thing that comes out of it. And on those, you're going to see you would actually end up looking at low radionuclide abundances will tell you that. So another interesting thing that just by measuring the stellar abundance, you might have some sense of what happened. Not a great sense, but you'd have some sense. All right, so I spent a lot of time talking about snowballs and degassing ending and no longer habitable. Let's talk about another end of perhaps no longer habitable and talk about hothouse climates. So in this plot, it's that same relative amount of heat versus now we're going to vary the mantle carbon abundance. For reference, the Earth on this plot is at about 10 to the minus 2 weight percent. But we can see some interesting things that were not exactly new. At low carbon abundances, your degassing lifetime is relatively short because you're essentially out of carbon. But as you start increasing your carbon abundance, these you don't really see any change anymore. It's kind of, and with mass, it's, yeah, there's really, the degassing ages are longer, all of this. What's interesting though, is if you start taking a look at how many of those planets for a given mass ended up having their degassing lifetimes, given a randomly chosen radionuclide abundance, end up in the hothouse regimes. Their degassing rate exceeded their supply limit, and they just tipped into hothouse and stayed there. So here, going right to left, this is just increasing mass, but you can see some interesting things that here's the Earth abundance of mantle carbon. So for an Earth mass planet, yeah, I mean, you're not really going to get a lot of models that are supply limited. But as you start increasing planet mass, if you even going up to 6 Earth masses, by the time you reach an Earth-like abundance of carbon, all of our models are supply limited. So they could still be degassing today, but they're degassing into an already hothouse climate. Now, I find this really interesting. So this is a mass radius diagram. And so we talk a lot about, when we talk about atmospheres in terms of demographics, we almost exclusively talk about things like mini Neptunes and water worlds. These are big, puffy, observable planets. On the other end of the spectrum, you have super dense things that may have an atmosphere, but certainly not a big one. Super Mercuries that are, but you have, and this is what I call the nominally rocky planet zone. This is sort of the densities you would expect based on stellar abundance distributions of, and this model encapsulates like 10,000 individual mass radius models. So anything that's colored here is likely to lie outside, but all these gray points in the blue, especially as you start getting up to this, say, 5 or 6 Earth mass things, these are in the range where we're predicting they should all be carbon rich on their surfaces, but their atmospheres may be thin enough that it doesn't affect their mass radius measurements. So this is, I think, an interesting crossover with this is, are these planets, can you do a demographic study, even if you just know the presence of an atmosphere, and that is presumably carbon rich? Can you predict anything about how the distribution changes with mass? And I think that's really interesting aspect of perhaps just not what the atmosphere is made of in detail, but just that it has one. And the fact that if it has a water-rich atmosphere, it's not in that. Any amount of water is going to push it down here very quickly. So these planets are interesting intermediate densities that may have something to say about, I think, this is now we're in speculation, but if you know something about the age and the presence of an atmosphere, are there lots of rocky exovenuses? We would call them rocky, but they could be exovenuses. And I think this is a cool next step for exoplanet demographics. All right, so I'll finish off with some open problems. The first one is, we don't need, I always say need, we really should have radionuclide abundances. We have the technology to do it. It's just a matter of time to measure the abundances of thorium, potassium, and europium, and magnesium and silicon to understand this. But especially age. Age is something I think for metal-rich stars we're a bit scared of, but it is a really key indirect, not even indirect, it is a direct observable that is going to tell us something about what we should expect for where in its geologic evolution it is. Is it old and dead, young and hot, medium? The potassium-40 ratio is super unconstrained. We need to know that, right? Or at least understand the distribution. And then the demographics with age. Right. Oh, and importantly, galactic chemical evolution models. Do these need to be updated, taking into account these elements that maybe aren't thought of as chemical tracers, but are very important for exoplanets. In geoscience, of course, I geared this talk to be a bit more astro-y, so I didn't talk about a lot of the geophysical problems, but viscosity is a huge variable in this. It's extremely unconstrained, especially at high mass. So and with composition. And there's been some work, this is from Rob Spargren, looking at sort of how viscosity changes with something like the magnesium to silicon ratio of the planet, but that's kind of where we're at. When we're talking about volatile pore states, we need to understand, well, you could have a volatile rich planet, you just don't see it because it's all locked up in the core where it will never get exposed to the atmosphere. So those are big geoscience questions I think we can maybe get a handle on. On the meteoritic planetary science side, this is of course where we start talking about depletion. How does planetary formation tie with chemical depletion? I think that's a really important. And then is this 5 times depletion, this 80% normal? Is the Earth just happens to have that? And of course, having some handle on the carbon abundance as we would expect. Now, this one I imagine is just all over the map because carbon is, yes, I think that one is going to remain constrained, but maybe are some constraints. So I'll leave out my conclusions here. Yeah, I'll go ahead and take questions. Thank you.
Okay, we'll take questions in a second, but first, so I don't forget, I'm gonna tell you that Cayman has some extra time in his schedule today and tomorrow. So if you'd like to meet with him, let me know and I can get you on his schedule. And we have 2 open spots for dinner tonight. So if anybody's hungry tonight, getting Italian food. So, okay, now we can take questions. So I'm not connected to the Zoom. So if you have questions on Zoom, you're gonna have to, I don't know, raise your hand or something like that.
Yeah.
We can find you. Maybe we can start with this in the room. I have a question. So one element that you didn't talk about is aluminum 26, which of course is important in the initial stages
Right.
of planet formation and the differentiation for kind of the building blocks of planets. Do you have a sense of how easy that is to measure in stars and how that might change planets as they form?
I don't have any sense, but I'm gonna guess it's very hard
Yeah,
It's very hard.
it sounds.
because its half-life is so short.
Yeah.
Half-life is like this big.
Now, I've often wondered if are there some ways we can measure potassium 40, not for planet hosting stars, but just in general. In conversations a long time ago, there was some discussion of perhaps in AGB stars, you can, through dust and isotopologs, maybe measure potassium ratio. But no, I think this is, at best, we're going to get the bulk abundance, and then we really have to rely on models that hopefully have observational, or there are theory papers that can be observationally tested. But I don't know about that. And so we just may have to rely on physics and chemistry to tell us how much it varies.
Yeah.
And then aluminum 26, I think that's really interesting because, you know, there's been work looking at how that sets your initial water abundance. And so perhaps those planets that were low in aluminum 26 are already water worlds and are not germane in this conversation at all. But the high ones, which may have been desiccated, are. So yeah, but that's another interesting demographics question.
What about iron 60?
I am extremely not well versed in iron 60. I know, is that an even shorter half-life than 26?
It's comparable, it's a little bit longer, but it's definitely a signature of supernova.
Oh, okay, cool. No, I don't know anything about
Okay.
Sean?
Yeah, so I'm curious on your age plot versus, your critical line,
Mhm.
and now you bring in possibility of tectonics or some tectonic flavor or tidal heating.
Yeah.
How would you move that line? How would you start quantifying the possible? I guess tidal heating might be the easier one.
Yeah.
Too, but.
Yeah, certainly tidal heating would be, and the thing I didn't have time to put in this talk is, which is in the new paper, is a lot of work Brad did on trying to get a sense of the critical heating rate you need to initiate and have long-lived degassing.
Hmm.
And so essentially then whatever energy source you want, get above that threshold, you'll be fine. But I guess I don't know. I think it's going to be, this is, I guess I didn't mention it. This is kind of a pessimistic model. So perhaps more optimistic models could come up with 1 billion years here or there. But I think we're going to really struggle to find 8 billion years in a pessimistic case.
Yeah, that was kind of the question. Is there, even with all of the tidal heating, is there any way that the Trappist planet
Yeah, I don't know.
can still be gas?
I mean, if they stayed hot,
Yeah.
right, this doesn't include the presence of an atmosphere. Well, it does kind of. There's probably more complex things you can ask, especially on climate feedbacks that are not included in this model that at least keep your surface hot. And so if your surface stays hot, your mantle can stay hot. But it's a balance, because if you're too hot, you may shut off convection, which now you're limiting material to the surface.
Yeah.
So you shut off degassing a different way. Yeah. There's also the question of overturn is one thing, because if you have, a slower return rate, that could change things. You just keep it around longer, but then you have to worry about your crust getting so thick, pressure is so high, you can't melt anyways, right? So it really is, plate tectonics does a great job of just the lithospheric thinning, that's what gets the Earth to degas so long. It's just the fact that we have thin lithosphere. So if you can find a way to do that, that would also.
So Trappist is an M star,
Mhm.
and that means that you gotta get the planets close to it to keep them warm, but it's got a lot of UV variability,
Mhm.
with a lot of energy coming out of there. And so the question is, are we hurting ourselves by looking at M stars with prime planets, because the environment we don't understand at all?
Yeah, I think that's an extremely fair point, and a landmine I'm gonna try to avoid. I think M dwarfs especially gives us the numbers. We can get, Natalie Hinkle has been working a lot on trying to get M dwarf abundances. So that'll be a big step, having a data set like that we can easily get for XGK stars. So while, like you said, they may not be the best case for habitability, especially if they're old M dwarf stars. The fact that TRAPPIST-1c is volatile poor, presumably, actually helps us constrain a lot about planetary formation models. And, so it may not be habitable. And I think this is where habitable is a concept that pigeonholes us a little bit.
Yeah.
Whereas planetary science, we can do with, we're spoiled in our solar system that we have rocks you can pick up, we have remote sensing data. We're never going to get that for an exoplanet. So as planetary scientists, we have to kind of think, well, you have those 6 or 7 observables. You don't have to tell the whole story of the planet. Just kind of say, the observers who kind of are running this thing, should they look at that one or should they look at that one? And try not to muddy the waters too much. But I think that's a really powerful thing to just kind of understand. It may be that M dwarfs are absolutely terrible to look at for life for a lot of reasons. But they may be able to help us better constrain planetary formation models in general, which I think is really, really powerful.
So there's about 24 planets being observed in the first 2 cycles of JWST, right? Just rocky planets that are being observed. Do you know what fraction of those actually have the kind of stellar abundances that you need to do this?
In my experience, probably none of them.
Yeah. They're basically all M dwarfs.
Yeah, there may be metallicity. There's almost always metallicity.
Yeah.
Abundances,
Getting that?
metallicity.
Well, should we be trying to get these abundances? Is that
hard to do it?
Yeah, I would love that.
Yeah.
It's funny. One of the reasons for this plot is to say, hey, somebody go get abundances for those stars. And yeah, and especially even on the planet formation side, I would love to know TRAPPIST-1's iron to magnesium ratio to help constrain its core size. its error bars are so small, I can actually do good mass radius models and constrain the system a lot more. And if you can constrain the first two, it's going to set big constraints on the other four. So abundances, I think, are really big. They're indirect, and a lot of people don't like them because it's so indirect. But I think that's missing the forest through the trees in a way of like how little information we have. You know, how much money is it going to cost to get a little bit extra? I think is important, especially once we get atmospheric measurements for regardless of what planet it is. Now it's the geoscientist's problem to figure out how it got there. And that is a whole area of infrastructure, and I didn't get to talk about it, that NASA is just now starting to fund. So I'm the deputy PI of ASU's TREC team, Tracy Rocky Exoplanets Compositions, and this was recently funded. We just got started, where we're trying to start from molecular cloud all the way up to first crust to try to track how the major elements move among different reservoirs and sort of at what order of magnitude. And so if phosphorus is an element that's key for life, what does it, phosphorus is an extremely metal loving element. So what happens if you just lock it all into the core? Or think these kinds of questions. So I think the geoscience work is getting started, but we've learned so much about the Earth that is barely useful for exoplanets. We have a lot of infrastructure, especially on the experimental side, to do to understand anything, I think. So I think abundances would be great. I think ages are more important because it is such a direct observable. I mean, even if it's, like I said, old or young, 2 plus or minus 2 is very different than 8 plus or minus 2. So I think that's a key thing that maybe we can get a handle on, especially for planets of high importance. And actually, I need to go back and look in the first 2 cycles and see if any of them are those 2. I forget. I don't think they are.
I don't think so.
Because this one does require mass, radius, and age to be on that plot. And so either they're missing, usually they're missing mass, and they're almost all missing ages.
Okay,
Right.
with that, let's thank Cayman again.
Thank you.
Really, you know,